This is the answer to homework 6, question 1. The question asks, they provide they say that x and y have a joint density function, which is written right here. It's fxy equals 1 plus xy over a when the absolute value of x is less than 1, and when the absolute value of y is less than 1, and then it's 0 otherwise. So that can be rewritten for the limits. X is between -1 and 1, and y is between -1 and 1. So the first part of the question asks us to find a value a so that this function is a valid joint density function. And so you set up the integral, and the integral should be equal to 1, and so then from there you would solve for a. So here we have the double integral of 1 plus xy, and then I pulled the 1 over a out to the front. And it's just a simple integral. I reversed the order of the limits, but you could do it the other way too. Then essentially you end up with y plus xy squared over 2. Evaluate that from -1 to 1. And then you end up with the integral of -1 to 1 of 2 dx times 1 over a. And that is equal to 4 over a, which is equal to 1, since I said the integral should be equal to 1 for a valid joint density function. Then you get a equals 4, which we'll use for the remaining parts of the question. So the second part asks if x and y are uncorrelated. So if x and y are uncorrelated, the covariance should be 0, and if they're independent, then they are also uncorrelated. So we have a couple different ways we could prove it. So the expectation of xy is equal to the expectation of x times the expectation of y. Then the variables are uncorrelated. And so we set up the integral so that it's expectation of xy is equal to our x and y limits evaluated from, here we have f of xy multiplied by x and y. And so when you solve that integral, these are all the steps, when you solve that integral, you should get 2 over 18, which simplifies to 1 over 9. And so that's expectation of xy. So then I evaluate, I want to see if that's equal to expectation of x times the expectation of y. So the next step I did was solve for the expectation of x. So for this, you only evaluate the function multiplied by x instead of xy. And when you solve for that, you actually get 0. And so there's actually no point in solving for the expectation of y, because we know no matter what, it's going to be, when you multiply them together, you're going to get 0. And so because these the two sides are not equal, so e of xy does not equal e of x times e of y, then we know that the two variables are not uncorrelated, which means that for the next part, when they ask if they're independent, they're not independent, because if they're not uncorrelated, then they can't be independent. And then the next part of the question asks us to find the joint density function of x squared and y squared. So to find that, you calculate the Jacobian, and when you set it up, you make x squared equal to z and y squared equal to w, which gives you 4 roots. So here you have root z, root w, root z, negative root w, negative root z, root w, negative root z, negative root w. And so when you solve for the Jacobian, when you calculate the partial differentials, you end up with 4xy, and then that's where you would sub in your roots. So here we have the joint density function being equal to 1 over the Jacobian times f of xy times az plus bw, so that's our x portion, and then the y portion is cz plus dw. And so that comes from the fundamental theorem. And so this is kind of what it looks like with the symbols, and so then we plug in all our numbers into that that expression, and because we have 4 roots, then we have 4 different segments to this. And so we have the Jacobian in the denominator, and then in our numerator, in each segment we have our different roots. And that ends up simplifying to 1 over 4 root z root w, for z varying from 0 to 1, and for w varying from 0 to 1. And then otherwise it's 0. And so to prove that x squared and y squared are independent, we kind of do what we did similarly to prove that x and y were independent. We get our marginal density functions, and so they're similar for z and w, but here's an example for z. So fz of z, going from -1 to 1 of 1 over 4 root z root w dw, that equals 1 over 2 root z, and then when you do the same thing for fw of w, you end up with 1 over 2 root w. And so those are our 2 marginal density functions, and ideally those multiplied to, if they're independent, those multiplied together should give us what we have here, 1 over 4 root z root w, and of course it does. So therefore x squared and y squared are independent, and that's the answer for question 1.